The Ring of Fire is not a mythic circle of flames around the Pacific. It is a broad tectonic belt, roughly 40,000 kilometers long, where Earth's crust is under constant mechanical stress. Around this belt, volcanoes and earthquakes are concentrated at levels unmatched anywhere else on the planet. That concentration is why the Ring of Fire matters. It links deep geologic processes directly to human risk. The phrase sounds simple, but the system is not simple. It includes continental margins, island arcs, ocean trenches, and zones where multiple plates converge in complex ways. It also includes both visible volcanic mountains and submarine structures hidden beneath the ocean surface. To understand this region, we need to shift from a map label to a process-based view. The Ring of Fire is best seen as an active boundary network where plate motion drives recurring cycles of deformation, rupture, and magma generation. Once you see it that way, the pattern of global seismic and volcanic activity becomes far less random and far more predictable in structure, even if exact timing of events remains uncertain. Scale helps clarify what this belt represents. The Ring of Fire is up to several hundred kilometers wide in places, meaning it is not a narrow fault but a geologic corridor with multiple active features. Estimates suggest it contains hundreds of active or dormant volcanoes, often cited as around 2/3 of Earth's total. Even more striking, about 90% of global earthquakes occur in this broader circum-Pacific system, including many of the largest known events. These numbers are not trivia. They show that the Pacific margin is where tectonic energy is being most effectively transferred from long-term plate motion into sudden releases. The same region can produce frequent moderate earthquakes, rare megathrust events, explosive eruptions, and prolonged aftershock sequences. In practical terms, this means the Ring of Fire is not defined by one hazard type. It is a multi-hazard environment, where different processes overlap in time and space. That overlap is why infrastructure planning, emergency management, and scientific monitoring in Pacific-facing nations must be integrated rather than siloed. A volcanic crisis can coincide with seismic instability, and a major earthquake can trigger cascading failures well beyond the immediate rupture zone. The engine behind the Ring of Fire is mostly subduction. At convergent boundaries, dense oceanic lithosphere sinks beneath another plate and descends into the mantle. As the slab goes down, pressure and temperature conditions change the minerals it carries, especially water-bearing phases. Those fluids are released into the overlying mantle wedge, lowering melting temperatures and promoting partial melt generation. That melt can rise, interact with crust, evolve chemically, and eventually feed volcanic systems at the surface. At the same time, the contact between the descending and overriding plates can lock for long periods, storing strain that later releases as large earthquakes. This is the crucial link. Volcanoes and earthquakes in this belt are not separate stories, they are parallel outputs of the same tectonic architecture. Subduction also creates deep ocean trenches where the plate bends and initiates descent, making the surface expression of boundary processes visible on bathymetric maps. So when we say Ring of Fire, we are describing a coupled mechanical and geochemical system that recycles crust, redistributes stress, and continuously reshapes the Pacific margins. Although subduction is the dominant pattern, the Ring of Fire is not one uniform boundary. Different segments operate with different plate speeds, slab angles, crustal compositions, and structural histories. Along parts of western South America, the Nazca and Cocos interactions with the South American margin drive intense seismicity and long volcanic chains. In the Northeast Pacific region, interactions involving the Pacific and Juan de Fuca systems contribute to a different mix of subduction and related faulting behavior. Across East and Southeast Asia, plate interactions involving the Philippine and Eurasian domains add further complexity, with arc volcanism, trench systems, and back arc deformation occurring in close proximity. Near Australia and adjacent regions, the geometry can become even more fragmented due to microplates and evolving boundary kinematics. This variability matters because hazard style changes by segment. Some zones emphasize giant interface earthquakes, others produce frequent explosive volcanism, and some generate complicated combinations of both. Treating the Ring of Fire as a single hazard model leads to poor assumptions. Segment-specific tectonic context is essential for realistic risk assessment, forecasting priorities, and policy decisions. The structures built by these boundaries are fundamental to how the belt behaves. At many convergent margins, deep trenches mark the point where oceanic plate descent begins. Landward of those trenches, volcanic arcs form above regions where slab-derived fluids promote mantle melting. In some settings, extension behind the arc opens back arc basins, adding another layer of tectonic activity. Over millions of years, these features migrate, shut down, or reactivate as plate motion evolves. A volcanic arc that is active today may not be active in the same location in the distant future. Likewise, extinct volcanoes within the ring record earlier phases of boundary configuration. This long-term mobility is why the Ring of Fire should be understood as dynamic architecture, not a fixed line on a map. Geologists read this architecture by combining seismic imaging, rock chemistry, geochronology, and plate reconstructions. The result is a timeline of crustal recycling and arc evolution that explains why some regions host dense volcanic clusters while others mainly express seismic strain. The present hazard landscape is therefore a snapshot of an ongoing tectonic film, not a static geological portrait. Volcanism in the Ring of Fire is often associated with stratovolcanoes, and for good reason. These steep, layered volcanoes are built by alternating eruptive styles, explosive phases that produce ash and fragmented material, and diffusive phases that produce lava flows. The magma feeding many arc stratovolcanoes is commonly andesitic to basaltic andesitic, though dacite, rhyolite, and basalt also occur. Why does composition matter? Because magma viscosity and gas behavior strongly influence eruption style. More viscous magmas can trap volatiles, increasing pressure before release and raising explosive potential. That can produce tall ash plumes, pyroclastic density currents, and widespread ashfall impacts. But arc systems are not compositionally uniform through time. Magma can evolve in crustal reservoirs, mix with new inputs, or interact with surrounding rocks, changing eruptive behavior from one cycle to the next. This is why historical patterns help but do not guarantee future style. Two eruptions from the same volcano can look very different if magma storage conditions changed. Monitoring gas emissions, deformation, and seismic tremor is therefore critical for detecting transitions that precede major eruptive shifts. Earthquakes across the Ring of Fire span a wide depth and mechanism range. The most famous are megathrust events on subduction interfaces, where very large rupture areas can generate devastating shaking and tsunamis. But many damaging earthquakes also occur within overriding crust, where shallower depth can intensify local impacts even at lower magnitude. Intermediate and deep focus earthquakes inside descending slabs add another layer, revealing deformation processes far below surface fault systems. This diversity complicates public expectations. People often imagine one earthquake type per region, yet real tectonic margins host multiple interacting seismic sources. After a major event, stress changes can alter nearby fault behavior, and aftershock sequences may persist for months. Ground response then depends on local geology, soft basins can amplify shaking, unstable slopes can fail, and lifeline systems can cascade under combined stress. That is why seismic hazard cannot be reduced to magnitude alone. Depth, rupture direction, site conditions, and infrastructure fragility are equally important. In Ring of Fire regions, resilient design requires planning for compound outcomes, not just single-event scenarios. The scientific challenge is to translate complex source behavior into practical, location-specific risk guidance. The Ring of Fire also has a long temporal dimension. Its recognizable circum-Pacific character extends back tens of millions of years, while subduction in some constituent sectors is older still. Through that history, plate boundaries have reorganized repeatedly. Arcs have migrated, collisions have modified crustal architecture, and older volcanic belts have gone extinct while new ones formed. These ancient features are not irrelevant fossils. They influence modern behavior by controlling crustal weaknesses, hydrothermal pathways, and thermal structure. In some areas, old faults become zones of renewed deformation. In others, altered volcanic rocks create slope instability that can amplify hazard during heavy rainfall or seismic shaking. Deep-time reconstruction therefore improves present-day forecasting by identifying persistent structural controls. It also helps explain why neighboring segments can display very different eruption frequencies or earthquake recurrence intervals. The takeaway is that current hazard emerges from both active plate motion and inherited geology. Ignoring the older framework leads to incomplete models. Integrating modern monitoring with long-term geologic records gives a more robust understanding of where energy accumulates and how that energy is likely to be released in future cycles. Even the boundaries of the Ring of Fire are not perfectly agreed upon, and that nuance is scientifically healthy. Some regions, such as parts of western Indonesia or the Antarctic Peninsula, may be included or excluded depending on criteria: active subduction, volcanic continuity, seismic clustering, or broader circumpacific tectonic linkage. This variation does not weaken the concept. It highlights that geologic classification depends on purpose. For global education, the Ring of Fire is an effective framework to describe concentrated Pacific margin hazards. For engineering or emergency planning, the framework must be refined to specific fault systems, volcano histories, and local exposure patterns. In other words, the ring is a strategic map, not a complete operational manual. Good hazard governance starts with broad concepts but advances through local detail. Which communities face tsunami inundation risk? Which slopes are most landslide prone? Which transport corridors cross vulnerable fault traces? And which volcanoes show current unrest indicators? Bridging scale from global pattern to local action is where science produces real safety benefits. That bridge is especially important in this belt because hazard intensity and population density often overlap. The societal implications are enormous. Many Ring of Fire regions include major cities, ports, manufacturing zones, and critical energy infrastructure. A single large event can ripple through supply chains, insurance systems, public finance, and food or fuel logistics far beyond the source area. Offshore ruptures may launch tsunamis that reach distant coastlines. Large eruptions can inject ash into flight corridors, disrupting aviation across continents. Recovery is rarely only about rebuilding structures, it also involves restoring trust, governance capacity, and economic continuity. This is why preparedness cannot be reactive. Effective systems combine hazard mapping, strict building codes, redundant lifelines, public drills, early warning networks, and transparent risk communication. Communities that normalize preparedness generally suffer fewer long-term losses than those that treat disasters as rare anomalies. The Ring of Fire is a reminder that geologic risk is permanent at human timescales. But permanent risk does not mean permanent vulnerability. With sustained planning and evidence-based policy, societies can reduce casualties, shorten recovery timelines, and protect critical functions even under extreme tectonic stress. In the end, the Ring of Fire is best understood as a living planetary boundary system, mechanically active, chemically productive, historically persistent, and socially consequential. It surrounds much of the Pacific not as a single structure but as a chain of interacting margins where crust is recycled and stress is repeatedly released. Its volcanoes, especially stratovolcanoes, reveal the geochemical signature of subduction. Its earthquakes, from shallow crustal shocks to giant interface ruptures, reveal ongoing strain transfer across plate boundaries. Its deep history explains modern complexity, and its modern impacts demand long-term resilience planning. If there is one core lesson, it is this: the Ring of Fire is not just where disasters happen, it is where Earth's internal dynamics are most visibly connected to human systems. Understanding that connection moves us beyond spectacle and toward preparedness. The science already provides a powerful framework. The practical challenge is applying it consistently before the next major event tests every assumption in real time. If you found this helpful, please like this video and subscribe for more explainers.